So this video is going to be just a quick recap for you. So you have already have graph representation uh, and also the BFS. So basically, in short, a graph is just a set of vertices and edges that connect them. Um, so here G represents the graph as a whole and V represents vertices while E stands for edges. Um, and we have mainly two types of graphs, and the first one is directed and the second one is undirected graphs. Pretty straightforward. So that basically means if we say this is a vertex A and this is vertex B, and we have an edge AB which connects these two nodes, then it doesn't have any direction, so that's why we call it undirected graph. Uh, and let's say for the same nodes, we have this kind of edge which is directed from A to B, and so this type of graphs are called directed. And in case of undirected graphs, that means you can go from A to B as well as from B to A. While in case of directed graphs, the direction means a lot. So this means there is only a way from A to B and not vice versa. So this is it about direction of the graphs. And also sometimes directed graphs are called as like they are denoted as d-graphs in these lecture slides. So if you see anywhere d-graph, just know that this is just a directed graph. And so now we know what is a graph, but how do we represent it in a memory of computer? So there are actually two ways of representing it. So this is a graphical representation and this is the textual representation, but this doesn't work in a memory of computer. So what we do, we have two options. The first one is to represent the graph as a adjacency uh, adjacent matrix, and the second one is as a list. So for example, this is the matrix representation of a graph, and here also we indicate the number, the existence of connection between two edges is number 1, and if there is no connection then we indicate it as 0. So we can call it like a bit matrix representation of a undirected graph. So here basically what does this matrix mean is so from 1 to 1 we don't have uh, any edge, meaning that this graph doesn't have self loop. If we put here 1, then that would mean there is some sort of cyclic loop or self loop on a vertex, but we don't have it, so we put 0 here. So there is an edge from 1 to 2, so we put 1 here, and there is an edge from 1 to 3, so we put 1 here, and there is no edge between 1 and 4, so that's why it's 0. And you can also know that this matrix representation of a undirected graph is always symmetrical. So in the main diagonal we have zeros always, and two other sides, lower and upper triangles, they will always be symmetric to each other. And here comes the adjacency list representation of a graph, which is one more way to represent the graph in a computer. So what does it mean uh, is just, for example, if we represent this graph as a adjacency list, we'll have, so as you see, this is a directed graph. So from 1 to 2, we have an edge. So we do uh, from 1 to 2, we add an element, linked list element, and since and here we list all the nodes that have uh, connection between. And for the second node, we have so it has an edge to 3 and 4. So we put it like from 2 has an edge to 3 and 4, and so on and so forth. So this is the idea. And in regard to the space complexity of representing graphs, so obviously adjacency matrix is gonna take much more space because of its uh, like its nature. So if you have let's say 7 nodes, then you're going to have 49 um, cells in the matrix. Uh, yes. So the worst. So this is the space complexity of matrix representation of a graph, which is big theta n squared. And for the adjacent cell list, it's much less. And here n denotes the number of vertices and m denotes the number of edges. So this is the space complexity for list representation of a graph.